Hello, everyone. Hopefully we are live. Welcome to the Khipu 2021 event series in AI. It's a real pleasure to have you all here for the second edition. My name is Fede Carnevale. I'm a research scientist at DeepMind. And today I'll be briefly telling you what we have prepared for this session. So for those of you who are joining today for the first time, Khipu 2021 event series in AI is a series of monthly events online, which are geared towards supporting the advancement of Latin American talent in AI. So each event will consist of 2 sessions. The first session will be conversations on AI, which are going to be wide-ranging conversations exploring the most critical unsolved problems in AI today. And in the second part, we will have applications of AI, where we'll see deep dives into examples of AI applications in the real world. So we plan to have 1 event each month. So stay tuned because at the end of today, we'll be announcing the next event. So I want to take this opportunity also to thank our sponsors for supporting this initiative and making these events possible. So thank you very much. And so for today, we have 2 amazing sessions on the topic of self-supervised learning. So first, we will start with a conversation between Yann LeCun and Martin Arjovsky on self-supervised learning and the future of AI. And in the second part, we will hear from Sandra Avila and Enzo Ferrante on applications of self-supervised learning to the real world, which will also include a panel discussion moderated by Stephanie Hyland. So we are very excited about these two amazing sessions. So with that, let me formally introduce the participants of the first session. So today's host is Martin Arjovsky. He's a postdoctoral researcher at École Normale Supérieure in the Sierra team, working with Francis Bach. He did his PhD at New York University, advised by Leon Botou. Originally from Argentina, he did his studies at Universidad de Buenos Aires. And during that time, he also interned at several places, including Google, Facebook, Microsoft, DeepMind, and Université de Montréal. In general, Martin is interested in the intersection between learning and mathematics and how to ground the different learning processes that are needed in different problems and leverage this knowledge to develop better algorithms. And Yann LeCun is the chief AI scientist for Facebook AI Research and Silver Professor at New York University. His research interests include machine learning and artificial intelligence with applications to computer vision, natural language understanding, robotics, and computational neuroscience. He's best known for the invention of the convolutional neural network, which are widely used for image, video, and speech recognition. Yann is the recipient of the 2018 Turing Award, together with Geoffrey Hinton and Joshua Bengio, for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. So with that, let me invite Yann and Martin on stage. And meanwhile, just a quick reminder that you can post questions in the Ask a Question box below. And you can also vote questions such that Martin can choose and ask Yann. So with that, I'll leave you with Martin and Yann.
Hi, everyone.
Hi. Thank you, Fede, for the introduction, and thank you, Yann, for being here with us. This is a great honor to have you here, and I'm excited for the discussion that's going to happen. So to start with, I wanted to ask you if you could give a brief description of what self-supervised learning is and why you're excited about it. And in particular, what do you think is going to be the most useful for?
Okay, I'll start by why I'm excited about it. So basically, if you look at how humans and animals learn, they seem to be learning much more efficiently than our machines. And they don't seem to be using anything like supervised learning or anything like that. Of course, there is some level of reinforcement learning, but it's becoming pretty clear through the practice of reinforcement learning that reinforcement learning by itself is just way too inefficient, too slow, requires too many trials to explain how humans and animals learn so quickly. And so the question is, what form of learning do humans and animals use? And when you look at baby humans or animals, they learn about how the world works by observation, by experimentation as well, but a lot of it is learned by observation. And we accumulate an enormous amount of background knowledge about the world just by watching the world, essentially, watching the spectacle of the world. And so the question is, what is the underlying learning process that happens? What is it that allows us to learn that the world is three-dimensional, that there are objects in the world that are independent, that there are objects that follow predictable trajectories and others, animate objects that don't, and predict how other people or animals will act, learn about intuitive physics, all that stuff, right? We learn mostly by observation. And so perhaps a principle would be one by which the learning process learns to fill in the blanks, predict the future, for example. So you observe what happens in the world, and then you try to train yourself to predict what's going to happen next. Predict what you can see from your left eye, given what you see from your right eye, or predict what you're going to see by moving your head 20 centimeters to the left. And if you do this kind of prediction, you will learn very simple concepts that, like the fact that the world is three-dimensional. The fact that the world is three-dimensional is the best explanation for how your view of the world changes when you move your head. Okay? Once you have that, you have objects. Once you have objects, you have occlusions. Once you have occlusion, you have things like object permanence, the fact that you know that an object that's hidden behind another one is still there. Once you have that, you have dynamics, you have physics, you have everything, right? So that's why I'm interested in self-supervised learning, because it's the type of learning that we see in biology. At least that's a hypothesis. Cool. And then what is it? Well, it's prediction, filling in the blanks. Okay, so now I answered the second question while answering the first.
Cool, fantastic. So the follow-up question I have for this is, do you think in order to solve these problems, like learning 3D concepts and all of this, do you think that we need an agent that's acting in the world, or do you think that we can learn this passively, like from input-output pairs? And do you see that the field is going to change towards more of an active direction than what we're doing?
Well, okay, so there are two basic interesting questions in AI. Okay, one is, how much can you learn by observation without actually acting? And it's an interesting question that has like theoretical consequences. For example, there's people who say, like, can you do causal inference? Can you infer the causal relationship between things by just observing without and Martin, you've been interested in this, obviously. Leon Boutou, Björn Scholkoff, there's David Lopez Paz. A bunch of people have been sort of interested in this question. Can you establish causal relationships just by observation? And the answer is yes in certain conditions. So that's the first conceptual question. How much can you learn just by observation versus how much do you have to interact with the world to be able to learn more about it? And then the second question is, can you learn common sense? So all the things you need to know about how the world works, without grounding. And by that, this is people who are interested in language, ask the question, can you learn everything about the world by just reading books or reading text, right? Or do you need to connect everything to some sort of underlying reality, right? Do you need vision? Do you need touch? Do you need, other senses than just text or speech?
So what do you think?
To that, okay, well, my answer to that question, do you need grounding, is yes. I think you do need grounding. Despite the fact that you can produce surprisingly impressive systems that are just trained from text. I think ultimately, if you want system to have any kind of common sense, you need them to know about the world. Okay, so for example, imagine the following picture. I tell you, someone is in a room. The room is locked. That person doesn't have the key. Is that person outside the room? Can that person be outside the room? And you answer no, because if you don't have the key, you have to you crash the door, etc. Right? But you need to have the common sense to know that a person cannot be in two places at the same time.
Right?
How do you learn this? By reading text. Now here is a simpler situation. I put a glass of water on the table, a small table, and I push the table. Where is the glass of water now? Now, obviously, we all have the physical intuition that the glass is going to move with the table because it's on the table. You cannot learn this by just reading text. No text in the world will tell you this, all right? And it's a very basic fact, right? So the amount of background knowledge you need to learn about the world to have common sense is absolutely enormous. And the problem is it's not a collection of facts, it's a collection of models. You have models of the world in your head. That's what you learn. That's what common sense is. Okay, so you need grounding. Okay, and then the second question is, do you need interaction? My answer to this is probably not as much as you think, because interaction is both expensive and dangerous.
Could you clarify perhaps the difference between grounding and interaction?
So interaction means, can I learn to dance tango by not actually practicing tango, by just watching people doing it, okay? And to some extent, yes, but probably not very well.
Probably not very well, yeah.
Can I? So that's one example. But can I understand that there is gravity, for example, that objects that are not supported fall by observation, or do I need to be able to take objects and throw them on the ground? And the answer is probably you can learn this just by observation. Now, but if you look at babies that are roughly 8 months old or 9 months old, that's about the time that they learn about gravity. And you put them on a high chair and you put objects behind them, in front of them. They will throw them on the floor and they will look at them. They do experimentation, but you probably learn about it without having to do it.
Wow, that's very interesting. So, do you think that in the near future we will see things more like kind of robotics with learning, or do you envision this interaction and this grounding, not necessarily like in things like robotics, but also like in commercial systems and things like this? What picture do you have perhaps of like what's going to happen next with this?
Well, so I think, you already have, so in the narrow domain of self-supervised learning, okay, there is a lot of applications of self-supervised learning, and I think the next speakers will talk about this. But every single natural language processing system now, high-end natural language processing systems, the Facebook Translator, Google Translate, all the content filtering systems on Facebook, YouTube, etc. They all use self-supervised learning, pre-trained self-supervised text systems. Transformers that are trained as denoising autoencoders, basically, right? For image recognition, it's starting. It's not so much there yet because the performance until very recently wasn't that great, but now it's starting to get really good. And so you start having systems that are deployed now in vision that are actually pre-trained using self-supervised learning. And the advantage of this is that you don't need a lot of labeled samples to train them. I think a lot of the big advantages of this will be in things like medical image processing, in content filtering, obviously, but also in medical image processing, in autonomous driving and driving assistance systems for cars and things of that type. So probably a lot of really interesting practical applications that will save people's lives, right? It's really really important. Now, in terms of like the interaction, the whole idea of like the field of robotics has been somewhat resistant to the idea of using machine learning, because the entire field was dominated by like, how do you write the equations to model the dynamics of a robot arm and model friction and do PID controllers and all that stuff, right?
Right. The papers were the models rather than how to learn them.
Right. So it's handcrafted models, and you had a similar phenomenon in computer vision as well many years ago. Not so many years ago, about 10 years ago. And that's been, largely replaced by deep learning. So the question is a similar revolution going to happen in robotics? And the answer is, in my opinion, yes. There's no question. And there are people in robotics who are really sort of at the forefront of this. Chelsea Finn at Stanford, Sergey Levin and Peter Avila at Berkeley, and there's a bunch of people at Facebook, at Carnegie Mellon, and in Europe who are kind of interested in really heavily based robotics on deep learning, essentially.
Cool. So in this thing, what do you think is the most critical problem in AI right now? Or like the thing that you would like to see solved from here to like the next 2-3 years, something like that?
Okay. All right, so I'm going to work my way back from like a faraway goal, okay?
Perfect.
Faraway goal is that we'd like machines to be essentially as intelligent as humans in all the domains where humans are intelligent. I do not call this AGI, right? There's a lot of people who call this AGI, artificial general intelligence. I do not believe in this concept of general intelligence because I think that human intelligence is very specialized. So I don't like the word AGI. Like, I don't think AGI is a useful concept. Human level intelligence is a useful concept, okay? Okay, now we're not gonna have, human level intelligence of, machines that can reason and, do mathematics and all that stuff unless we build them specifically for this. But as part of sort of a generally, general learning, we might want to start with, slightly less intelligent levels, like say a cat. A cat is pretty smart. A cat has only about 870 million neurons or something like this. It's about half as much as a dog. It's about 100 times smaller than a human brain, but they're pretty smart. They're really, really good at intuitive physics. If you observe the cat, they run really fast. They have really good vision. So let's say we want to, have the same kind of learning as a cat. So a cat can learn a lot about his own dynamics when he's a baby, about catching other animals, predicting their trajectories and stuff like that. They can do causal inference, like some cats can open doors and stuff like that. I mean, they're pretty good at all this. So if you can reproduce what a cat can do, we're on a pretty good path to reproducing what humans can do. It's probably a relatively short path from there. So what can a cat learn? So a cat learn, that word 3-dimensional, they learn all the concepts, all the common sense concepts that I talked about earlier. A cat has a incredible level of common sense compared to all the most intelligent machines that we have. What type of learning do they do? So they learn to predict, certainly. In my opinion, the ability to predict is really the essence of intelligence. So they can learn to predict, their own trajectory, what the trajectory of a small animal they're chasing is, things like that. They can predict the effect of their action to some extent. So they build this model of the world, by observing and acting in the world. How do we reproduce this with machines? Now, here is the main technical question. So now you take that one level down, and you say, okay, I'm going to train a machine to just watch YouTube and predict video because that's the way the machine is going to learn about physics, right? The problem is the world is not entirely predictable. There's a lot of things that can happen. Like you're watching me right now. I could say one word or another. I could move my hand this way or not. I could turn my head this side or that side. You cannot really predict exactly what I'm going to do. So if I ask you to make a single prediction for, what I'm going to look like in the next second, the best thing you can do is basically predict the average of all the possible images of me, doing all those actions. And that would be a blurry image. So what you have to do is find a way to train a machine so that it does not make one prediction, but it makes, it predicts a distribution or something like that, the probability distribution. Now, we have no good way of representing probability distributions over images or, video frames. Not
what
really.
Do you think about generative adversarial networks, like the recent, let's say, more likelihood-based models and things like this? You want them to be substantially better, let's say.
Yeah, they all suck. I mean, they're really bad. So GANs are good for generating images to some extent as a way to learn like good features or learn how the world works, to learn representations. The results have been very disappointing.
So what do you think is missing? Is it missing some inductive bias about the structure of the dynamics, or is it just a general learning principle? Where do you think it's the path?
I think what's missing is a principle to represent uncertainty that is weaker than probabilities, because probabilities are intractable when you deal with high-dimensional continuous spaces like images. And so one thing I've been advocating for this is what I call energy-based model. So an energy-based model, so you have you have a variable you observe, X, think of it as a video clip. And then I give you another variable, Y, which is another video clip. And I ask you, is this second video clip Y a continuation of that first video clip X, a plausible continuation? And what that model is supposed to do is that it gives you a low number if Y is compatible with X, and a higher number if Y is not compatible with X. Okay, that's called an energy-based model. It measures the incompatibility between two variables, and the nice thing about this is that it's an implicit function. So what that means is that there might be multiple y's that are compatible with x. There might be multiple y's that are a perfectly good continuation of the video clip x, and your system will give it low energy for all those things. So you can think of energy models as kind of weaker forms of probabilistic models. Like a probability model gives you a distribution over y's. Here, what I'm saying is I'm giving you a score for all y's. Okay, whatever y you give me, I'll give you a score for it.
Right.
But I don't insist that those scores integrate to 1. Okay, I don't insist they're positive, first of all, but I don't insist that they integrate to 1, which is a condition for probability densities.
So I guess there's two main differences between an energy-based model and a probability distribution. The main one being the fact that it doesn't need to integrate to 1, and the second one being this implicit part, let's say. But how is this different from, like, for example, a generative adversarial network that has a discriminator or something like this, and you use this as an energy function? Because I remember there's been many papers, including one from Jake and you guys, on this.
Yep.
Why is this not enough, let's say?
Right. Okay. So that actually connects with some work that you did.
Yes.
So you have.
What do you think is missing even from that, let's say, and from like this? Like, why can't we use our current generative models to measure uncertainty? What do you think is something that perhaps is missing in there?
Okay, so I think there's a big fallacy, which is that GANs actually don't model probabilities.
I totally agree on this. Yeah.
Okay, right. I know you do. So in a GAN, you have two networks, right? You have the discriminator, sometimes called the critic now, and the generator. And you can interpret the discriminator or the critic as an energy-based model. Basically, you can think of it as a thing where you give it, let's say, an image. If it's a good-looking image, it gives you a low energy. If it's not a natural-looking image, it gives you a high energy. And you can train it, by giving it good images and bad images. That would be called contrastive learning. So contrastive learning is a form of energy-based of training an energy-based model, where you give it a good example and you tell the energy-based model, give it a low energy, and then you give it a bad example, something that doesn't look like a good image, and then you push up the energy of that guy. And what that does is that it trains the energy function to give low energy to good stuff and high energy to bad stuff. Now, the next question you have to ask is, how do I generate the bad samples? And in probabilistic modeling, people have used Monte Carlo, McCutcheon Monte Carlo, all kinds of different methods to generate those bad samples. There is a technique, in NLP, those transformer BERT style models.
Right.
What you do is you take a piece of text and you just remove some of the words. Right. It's very simple, but that's basically a way of generating a bad sample, whose energy you're going to push up. You can interpret denoising autoencoders as energy-based models as well. Yeah. Now, in GANs, you train another neural net to generate bad samples. Okay, so the generator is actually kind of a useless piece of neural net, which eventually people use, but that is just there to generate bad samples whose energy you're going to push up.
Right.
And if you're only interested in sort of training your energy-based model, you can throw away the generator. But in fact, in most GANs, people actually use the generator to generate images, and they don't actually use the critic that much afterwards, even though that would be kind of, in principle, the most useful part of it.
Well, I think it depends, in the sense that once your generator becomes good enough, the critic will just be distinguishing between like real and real. So there's an argument that you can make.
Between good and less good. But okay, now what you want, and in fact, this connects with your work. So what you want is this energy function that the critic produces to be somewhat smooth, okay?
Right.
You need it to be smooth because that's the only way. You need gradients of that function to be able to train the generator. So you want that function to be smooth. If you use the GAN in the way it was originally formulated, the GAN wants to produce a very non-smooth function. The discriminator wants to produce a very non-smooth function. And in fact, it leads to like mode collapse and stuff like that. So one trick, which is your trick, is Wasserstein GAN, where you say, okay, I'm going to regularize the the critics so that basically the gradient, the slope of the function is limited. I'm going to clip the weights or whatever technique so that I'm going to make that function smooth. But if you do this, you completely throw away the probabilistic interpretation. It's just an energy model.
Yeah. I guess one thing that is really perhaps a bit different from the traditional probabilistic thing as well is that you're only distinguishing between your generator and the real. You're not distinguishing from everything else. So I guess one thing that's really missing in GANs in this sense is like a calibrated uncertainty from everything that's neither real nor fake, because that's for everything else you have no idea. So I have a question from the audience, unless there's something you want to say,
well, I just wanted to say that maybe we have to abandon the idea that we need calibrated probabilities.
I totally agree on this. Maybe just Justin won't, but we can ask him at a later point. Okay, so a question from the audience. What's your opinion on diffusion models? Do you think they solve the problem of representing distributions over images, or why not? What is your take on like kind of the latest, perhaps this direction of likelihood-based models, or if you have any particular thoughts? Otherwise, we can change to something else as well.
Well, I think there is a lot of models that are really sort of interesting conceptually, but I think probably are going nowhere in practice.
Agree.
Or maybe they have applications in sort of narrow domains. So an example of this is normalizing flow type models, where to make them work, you have to really put a lot of structure in them. And that sort of limits their power. They don't scale very well with the dimension. I mean, there's a lot of limitations, but they're useful to people doing physics, for example.
Right.
So I don't think those models. I mean, there's things like score matching, and I mean, there's all kinds of methods, right, to sort of estimate functions that sort of tell you the difference between good things and bad things, whether you interpret them as energy or not. I don't like the constraints that are necessary for most of those things. So I think they can be useful in some narrow domains. I don't think they are the ultimate answer to like how do we do self-supervised learning or anything like that. Right.
I think the nice thing about self-supervised learning is that it's a very simple concept and it's general and it scales very well. And something that we've been seeing is that the things that are more applied lately tend to be particularly simple, like clip, for example, and things like this. They tend to be simple enough that they can later be general and applied on many things. I apologize, by the way, for the echo. It seems.
It's my fault, actually. I think it's.
Really?
I think it goes through my microphone. So I'll mute myself when you speak.
Okay, maybe that will do it. Oh wait, yeah, it's actually gone. Okay, cool. Thank you. Perhaps moving away from the technical discussion, since it will be, since we have you here, it's a shame not to get your advice on other things, perhaps more about what do you think now? I've heard you talk a lot before, and obviously you have a very interesting take on the differences between academia and industry and these kind of things. And you've said many times that the importance of research in industry for industry, right? How much industry benefits from having a pure research lab, like Facebook, the Bell Labs, all of these places. So do you think that value in machine learning is diminishing in the sense that, so to paint you a clearer picture of what I think, of where I'm coming from, like, in 2014, there were very few people that could train a COMNET in an applied setting, like in a very large scale, right? So the value of having like you or Jeffrey Hinton or Alex Krzyzewski and all of these people was very large, right? Now with PyTorch and all of these things, it seems that it's more accessible, right? So do you think that the value of having a research team in industry has diminished? And more in general, what do you see as the future of these collaborations between academia and industry in the future?
Well, okay, to answer directly your question, it's a moving frontier and it's moving really fast. So the way science and technology progresses is that once you discover kind of a new way to do things, you you make it easy for others to reproduce by building tools, right? So the first people to kind of come up with the technology not only build the widget, but they also build the tools to build the widget,
right?
And they learn to use it, right? If you are the first person to build an airplane, you have to figure out aerodynamics and stability. You have to learn how to fly your airplane the first time you put it in the air. You have to invent new fabrication techniques, and you have to build your own propeller because you can't buy it from anywhere, right? So it's a bit of that phenomenon, and it's true that until about 2013, the number of people who could train a convolutional net was very small, but not because I was smarter than them or anything like that, but because I built my own tools. So back in 1987, I was finishing my PhD, and I met Léon Bautou, whom you know well because he was your advisor, and he was still finishing his master's, basically engineering in France. And he said, I need to do a project, and I want to work on neural nets. I find it fascinating. We're talking 1987, right? And I said, well, I'm writing a simulator for a neural net, and I need a front-end language, because back then you didn't have Python, you didn't have any of that stuff, right? So you had to write your own interpreter, your own Python-like language if you want. So I asked him to write a Lisp interpreter, which he wrote in 3 weeks.
Pretty good code.
Typical Léon, okay. And so we started collaborating, and we wrote this neural net simulator, which at the time was called SN, for simulator neuronal. Okay, that's French, and that's what I used for decades after that. And it was a tool that nobody else had, and it had all the things that you see now in PyTorch. In fact, this tool essentially invented all the techniques you now see in all the PyTorch, TensorFlow, all those things. They use this idea that you can assemble blocks, modular blocks, and do automatic differentiation by inverting the graph. And to write a block, you just need to write the forward prop and back prop functions, which are very simple to write. And then you have this enormous tool. And we had this tool in the late 80s, a more refined one in the early 90s, and allowed us to do things that nobody else could do. And then by the mid 90s, nobody was interested enough in neural nets to actually start to learn those tools, so after I joined NYU in 2003. The students who were working with me and took my class basically had to learn this, because that was the tool. There's many of them at DeepMind and Facebook and Google now, and they could train convolutional nets, like everyone now can train a convolutional net because the tool was available. So that's like a big part of it. Now, the sad thing is AT&T did not allow us to release that code in open source before 2002, basically when we left AT&T, which is what we couldn't share that tool. We couldn't tell people here's code and you run this and that's a conv net.
Right.
So that made it difficult to kind of disseminate our ideas. That's one of the reasons why neural nets actually were not so popular for a long time. Okay, now to answer your question about industry. I spent half my career in industry, half in academia. Those two worlds are complementary, very complementary. There is a natural evolution of a technology when it becomes practical and there is sufficient commercial interest. It basically gets taken over by industry, and there's no point in academia to kind of help with it, because you're not going to beat the record on some translation competition or speech recognition if you are in academia. It's just it's just too hard. But most of the good ideas still come from academia. Okay, so what you have to do in academia is come up with new concepts, new ideas, perhaps new tools, new ways to kind of do things, new ways to do automatic differentiation, compiling neural nets or whatever. That's on the tool side. New hardware, if you are into this, and perhaps new algorithms, new methods, new techniques. You're not going to beat any record, but that's okay. Other people will do this after you, and they'll cite your work.
Cool. So
now, I have a story I must say about tools.
For it, yes.
The successor to SN was called Lush, and that was the open source version, and it had like a Lisp interpreter as a front-end language. And then the successor to this, which I didn't have anything to do with, which was originally written by Renaud Colobert and then Corey Kebucholu and a bunch of other people, Clément Farabet, was called Torch. And Torch, as a front-end language, used Lua, which is a Brazilian language. Okay, so that's an important role of South American computer science in deep learning. Torch was based on Lua. Eventually, PyTorch kind of replaced Lua by Python because that's what people want. But I was very sad actually because I like Lua.
Oh, come on! I mean, I like Lua as well, but it was a bit annoying sometimes. All of these default nil initializations and stuff. But yeah, it's certainly useful. Okay, so you touched on the topic of open sourcing and the importance of making your tools widely available for people. What do you think about the analogy that people say, for example, of like the Large Hadron Collider in physics and things like this? Like there are experiments that are not reproducible that you cannot just open source, but still have value to the research community. Do you think there is such a case for non-open sourceable or non-reproducible experiments in machine learning? Or you think it's just kind of an excuse? Or what is your take on like non-open source? Do you trust these results? Not?
No, I mean, I think there is a place for research, that outfits like OpenAI and to some extent DeepMind have specialized into, which is sort of very large scale. I mean, Facebook has been doing this as well, of kind of scaling up existing methods to the point where you can have sort of a splashy demo that kind of changes the way people think about a particular approach, right?
Right.
Everybody knows about language models. Everybody knows about neural language models. Yoshua Bengio, started doing this back in 2000, a long time ago. Everybody knows about transformer-based language models, blah blah blah. But if you scale this up to the size of GPT-3, there is something that emerges that seems surprising. I don't think it's particularly useful, actually, not in its current form, but it's an interesting experiment to do. Same with the OpenAI Rubik's Cube type robot hand, which is sort of sim to real type transfer. I don't think it's practical in any sense of the word, but I don't think you're going to be able to use any kind of techniques that are similar to this for, say, training a car to drive itself or anything. But there are experiments that you should do, like AlphaGo and things like that. It's interesting. I don't think they bring a lot to the table of like new techniques in AI research. They just inspire people sometimes, and they sort of illuminate the power of some techniques. So, yeah, I mean, I think there's a place for it.
Cool. So I'm gonna go with a question from the audience, and I think it's a great fit for you because you have talked about this particular metaphor many times. So you stress the importance of learning how humans do, and you can make the counter argument, which is that the current form of airplanes doesn't really follow birds, but you should perhaps be learning or producing aerodynamics rather than like just imitating how birds work. What is your opinion on this kind of argument and this line of thinking?
Yeah, it's a particularly important question for AI because there's kind of two extremes in the way to approach AI, right? There's one extreme which is sort of classical AI, if you want, of let's get a little bit of inspiration from the brain, but really what we should reproduce is logical reasoning and manipulation of symbols and things like that, right? Sort of high-level reasoning type tasks. And then there is an approach so this is only kind of modeling a small part of the human mind, really, and completely ignores like everything that animals do, right? And then at the other end, there is people who are trying to copy the brain in the most minute details, in the hope that if you copy every detail, then somehow and you simulate a large enough network of simulated neurons, AI will emerge from it. I think both are flawed. Okay, so the traditional AI approach is flawed because it basically completely ignores the importance of learning. And learning is very, very important. And the problem of learning is that it doesn't deal very well with discrete things like symbols and logic. And in fact, you realize that a very small amount of animals and even a very small amount of humans can do logical reasoning. That didn't pop up in humanity until a couple thousand years ago. So I think that ignores too much about intelligence to be able to work. The other side ignores too much about what's important, what's the underlying principle behind intelligence. Okay.
Right.
So if you use the aviation analogy, there were people in the end of the 19th century that tried to basically build airplanes by reproducing birds. Sometimes by flapping wings, not always. Sometimes by having wings that are shaped like bat wings or something like that. In fact, there is a famous pioneer of aviation in France that gave the name, actually. Okay, so the name avion, right, means airplane in French. In Spanish, I guess in Portuguese, there is a similar one, right? Avion.
It's the same in Spanish.
Yeah. The guy who coined that word is a guy called Clément Ader, and he was a pioneer of aviation in France, and he built a bat-shaped airplane that took off on its own power, steam-powered. Now, he's not very well known outside France. I guess in South America, Santos Dumont better because, he came several years later, but, he actually flew. And the reason you don't know about him is because, he was trying to stick to biology too closely. He reproduced, bat wings and everything, and did not actually did extensive. He had two issues. The first one, he didn't do extensive trials with gliders and kites and stuff like that, and experimenting with stability and control, the way the Wright brothers did and Santos Dumont, for example, later. So he was kind of hypnotized by biology, trying to reproduce too many details without really understanding the underlying principles, if you want. And the second thing is that he was kind of secretive. And so he was paid by the army, and, he didn't talk too much about what he did. And so a lot of people didn't believe he had flown, it's very controversial. So it points you to two mistakes you don't want to make, right? The first one is get too inspired by biology, and the second one is being too secretive. You really want to talk about what you do. You'll find that people will not steal your ideas. You're going to have to shove your idea in, down their throat if you want them to, get interested by them. So you want to basically discover the underlying principles behind flight, and then use those principles. And the principles that are used by airplanes to fly are the same that are used by birds, right? You generate lift by propelling yourself through air. And you have an airfoil and angle of attack, all that stuff, right? So it's the same principle. And so you can see that also in the history of technology and science, the technology, the artifact, very often comes before the science and the theory. The best example of this, there's like a dozen examples of this, but
I remember this slide that you made. It's great.
Right, but the best example is the steam engine. So the steam engine was invented, in the late 1600s. And then kind of refined, by engineers for 100 years. And thermodynamics that really explained the limitations of thermal engines was not really kind of understood until the early 1800s. It took over 100 years for the theory to really kind of come up. And the theory was developed to explain the steam engine,
right,
and figure out its limitations so that we could optimize it. But it became the basis for all of science, right? All of biology, all of physics are all based on thermodynamics.
Yeah. And I guess the nice thing about science and theory is that it provides a refinement of the things that are important, and it gives you some focus as well. For example, in chemistry and alchemy, I remember it's another example that you had. It's very clear to see the impact that chemistry has had on this kind of stuff. We try to discover new things and so forth. And I think this is a great part of the discussion. Perhaps you can relate it if you want to the next question that I'm going to ask, which is also coming from the audience. But so another question is, why are neural networks trained with gradient descent the correct tool to achieve this human level intelligence? Or I guess in general, the rephrasing, do you think that this is the a big part, or do you think that it's going to be refined once we understand these things a little bit better?
It's really a great question. So maybe it's a lack of imagination, but all the decent learning algorithms that people have come up with over the last several decades are all based on this principle of minimizing some loss function, right? Very often the loss function you minimize is not the one you actually want to minimize, but they're all based on minimizing some loss function. There are learning algorithms, from way back that are not based on minimizing a loss function. It's just a learning rule that says this parameter is changed with this rule, and I don't know if it converges. I don't care. It just does something. Okay. And so that's when the first big question you have to ask yourself: is this principle of minimizing an objective function a good one? Is it the case that the human brain or the brain of animals minimizes some objective? So objective that's probably computed by the basal ganglia, which is the piece of our brain that tells us if we are happy or uncomfortable or in pain or whatever. Okay. It could be that this piece of our brain computes our level of comfort or unhappiness, and the rest of our brain is there to basically minimize that. Okay. So that could be what's going on, but perhaps not. Now, if you accept the fact that learning proceeds by minimizing some objective, directly or indirectly, how are you going to optimize it? You have the choice between zeroth order methods that basically don't assume you can compute a gradient, or gradient-based methods, or more refined methods that use second order properties or some other property of the objective function. Now, gradient-based methods are enormously more efficient than gradient-free methods. Sometimes you have no choice but use gradient-free methods. But whenever you can, you should use the gradient-based methods. So in my opinion, there is so much advantage to using gradient-based learning that it would be crazy not to do it. Okay, deep learning is nothing. Okay, maybe you disagree, but
no. I agree, but I want to play devil's advocate in this because I've heard this argument many times. But couldn't you say the same for second-order methods versus first-order methods, in the sense that if you have Hessian information, why not use it?
Well, but there the argument is not that strong, because second-order methods, first of all, are considerably more expensive per step.
Yes.
Okay, require more hardware, more computation. They don't scale with the dimension very well. Right, they're all order n cube or n square, n square or n cube. Except LBFGS and stuff like that. But there's only a marginal improvement, and they don't seem to be actually bringing a significant improvement for things like complex deep learning. You need stochastic gradient, so that rules out a lot of efficient methods. So I'm not saying that that there is no kind of smart way of doing optimization, like momentum and all that stuff, right? Normalization of various kinds. There's all kind of tricks, right? They can accelerate gradient-based methods. But I'm saying, if you're asking the question zeroth order versus first or more,
right?
My money is on first or more. Okay.
And I guess the argument that you made is pretty solid, in the sense that at least if you say first order information essentially has the same cost as updating the parameters, because you have to iterate through all the parameters, so at least the computational cost is not is essentially the same, then why not use it?
Yeah, exactly. And
cool.
And gradient-free methods are actually very expensive because you have to do perturbations. It's ridiculous. So so my money is on gradient-based learning. So what that means is that because deep learning basically is just gradient-based learning applied to complex structures where you can compute the gradient or approximate it, deep learning is here to stay. That's part of the solution, in my opinion. It doesn't mean that the tools that we have at our disposal currently are sufficient, okay, which is why I'm sort of working on self-supervised learning, all that stuff. But deep learning is, in my opinion, part of the solution.
So I have another question from the audience that I'm gonna slightly add my little follow-up question as well. Or I'm going to make a slight difference. But so the question is, are we fundamentally missing other inductive biases to encode in the architecture? And particularly for the case of self-supervised learning or predictions. And I want to add my little take in here, which is, what do you think that the current inductive biases are enough for things like algebraic thinking, like parity, addition, discovering the shortest path in a graph, this kind of discrete predictions and discrete ways of reasoning.
Right. Well, shortest path in a graph, I think it's relatively easy. I think you can do this with analog neurons, actually.
I don't know if I agree with that.
No, you can. You totally can.
Even and learn it in like very small graphs and then generalize to like arbitrary length graphs, like Dijkstra does, or
so
size n to size
make a
n.
graph. Make a graph. Okay. And at each node in the graph, so you dynamically set up a neural net where each neuron is a node in the graph, and each connection is actually an arc in the graph. Okay. And the weight on your graph is actually a delay for a signal. Okay. So it's going to delay the signal, the propagation of the signal through it. All right. Now, so now you have a graph that's basically a neural net that is dynamically configured, and you put a spike at the input. Okay. And you wait for it to propagate to the end. And the time it takes for propagation is the shortest path in that graph.
Right.
Okay.
But
it's trivial to do analog with spikes and with delays. So,
yes.
But anyway, that's a side question.
Okay.
So the question is, do we have the elementary circuits that are necessary, or the architectural concepts that are necessary for everything? So maybe yes and no. So it's interesting that people are kind of discovering, new tricks every day, right? So there's the convolution trick, and then you can generalize this to convolutions on graphs, and then you can generalize this to like neural nets on graph, blah, 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 right? Geometric deep learning, right? I think it's a fascinating area. You have other elements that are, things like three-way multiplication. So you have two variables, you multiply those two variables with each other, you multiply that by a weight, which you can interpret as one variable determines the weight that connects the second variable to the, to the neuron, or whatever it is that you want to call it. People call this attention, but this idea of multiplicative interaction has been around since the 1960s for polynomial classifiers and later for so-called sigma pi neural nets. If the outputs of a bunch of neurons go into a softmax, then you call this attention because you have the coefficients are normalized, and then there is self-attention, blah blah blah, which makes it independent of permutation of the inputs, which is what transformers are based on. So there's a lot of ideas there that I think are fascinating, really interesting. But I think this elementary component of modulating a neural net by another one, essentially, right? So having a neural net that computes the weights for another neural net,
right?
Of which multiplicative interaction is sort of the elementary thing you need for this. I think it's a very interesting concept. People have given names to this that, like
hyper networks,
yeah, but I mean, whatever. I mean, the concept, there's like, like mixture of experts, that go back to the 90s that were kind of similar. So I think this concept is very powerful. I think it's actually essential for intelligent machines of the future, because I think there is something like that going on in the human brain. So this kind of connects with my theory of consciousness, which I will only talk about if you ask me.
If you can summarize it in like 30 seconds or 1 minute or something like this.
Okay. All right.
Just give us the TLDR. What is the one sentence?
I was talking about the fact that we need models of the world, predictive models of the world, to be able to predict the consequences of our actions, to plan ahead. So planning is a form of reasoning. In fact, it's probably the main form of reasoning that we do. For this, we need a model of the world, right? So let's imagine you're sailing. You never sailed before, or you are an expert sailor, but you imagine the flow of air on the sail and the flow of water on the fins and all that stuff, right? And that's what kind of allows you to be a really good sailor. You're in your workshop and you want to build a little box out of wood, right? You have to plan ahead, like, what kind of wood do I need to cut in what way so that I can assemble my box and put nails or screws or whatever. You're driving, you're next to a cliff. You know that if you turn your wheel to the right, you'll fall off the cliff and nothing good will happen, because you have a model in your head of intuitive physics, and what would happen in that case. And so you don't do it, right? So common sense is a collection of models. And when we pay attention to a particular task, we run a predictive model of the situation at hand. But here is the thing: we only have one such engine to be able to simulate the world in our prefrontal cortex. Prefrontal cortex is like the front half of our brain, right? This is really what makes us really intelligent. That's what allows us to predict. And we only have one engine that allows us to simulate the brain. That engine is configurable by another piece of our brain that basically says, now you're going to simulate the sailboat. Now you're going to simulate the car you're driving. Now you're going to simulate the mechanics of how you assemble this box that you were just talking about. And because we have only one, we need a system that configures it to the situation at hand. And that's what consciousness is. Okay, it's a cool. Crazy hypothesis. Don't take this as kind of a scientific theory or anything. It's kind of a bit of a crazy thing, but basically that would be a theory of consciousness where consciousness is a consequence of the limitations of the hardware of our brain. If we had a big enough brain to have a model of every situation we encounter, we wouldn't need consciousness. We need it because we need to deliberately configure our world simulation engine to the situation at hand.
Right. I guess efficiency comes from constraints a lot of times.
Right.
Exactly. So they're telling me that we have time for one more question, finally. So sorry, I rushed you. This is a question that actually I remember reading in your AMA in Reddit a while ago before I was in your lab, and I have to say it was quite helpful. Let's see if you have changed maybe the way you see this. But so what is an advice that you would give to a student starting his or her PhD or master's right now? What do you think they should do or learn, or how do you think they should think about their career, perhaps? What advice?
Well, I mean, there's no single answer to that question because it depends a lot on what you are actually motivated by, interested in. You know, do you want to do research or not? Do you want to like build things that are useful for people, or do you want to invent new techniques? You know, are you okay with the sort of academic circuit of publishing papers and stuff like that, or are you more interested into actually building stuff? I tend to do both, right? I'm both a academic researcher as well as an engineer. I consider myself both. So it really depends. But I think a good thing is to be ambitious about yourself. So basically, to make choices in your career that are the riskier, in the sense of they are the choices that you are least likely to regret not taking. Let me take a concrete example. I've met a lot of people who came to me and say, oh, you know, AI is really cool. I had a chance of doing a PhD 5 years ago, and I didn't. And now I regret it. I've never, ever seen anyone coming to me and said, like, I did a PhD and it was a complete waste of time and I really should not have done it. What it tells you is that you have some probability of regretting not doing something, but you rarely have, you know, regrets doing it or taking the risk of doing it. Of course, you know, it depends on your particular situation, but you should try to kind of, you know, be ambitious. The second thing is you should try to learn techniques, mathematical techniques, for example, that have a long shelf life. Things that are basic techniques that you don't know are going to be useful, but you know they're not going to be invalidated by, you know, something new. So if you have a choice, you're an undergrad, and you have a choice between, you know, taking a course on, you know, mobile device programming or quantum physics, you take quantum physics. Okay, and you might think that quantum physics is irrelevant to, you know, you're interested in AI, and why should you study quantum physics? Turns out all the mathematics that you do in quantum physics, particularly or in statistical physics, is the same that you use for, you know, inference in energy-based models or variational approximation of, you know, lower bounds for, you know, variational methods in graphical models or variational autoencoders. It's the same math. It's math that you learn in physics. In fact, the math that is most useful to learn for machine learning is what you learn either as a physics undergrad or as electrical engineer undergrad, or other engineering disciplines, actually. The kind of math that you learn in computer science is not a good kind of math, actually. So I would advise against majoring in computer science. You want to take a lot of courses in computer science because you want to know how to program. But if you're interested in AI and machine learning, you should probably major in W or physics or something like that, and take a lot of computer science courses, and then do a graduate program in machine learning, in CS, in data science, in things where you'll be able to really work on that. But take quantum physics, take statistical physics, take algebra, take probability theory from the kind of operator, complex analysis if you can, this kind of stuff, right? You learn something from it a lot.
Cool. I have to say you're extremely consistent, because the answer that you gave, I think 6 years ago or something like that, was take as much physics and math courses as you can. So
yeah, I haven't changed my mind about this.
Awesome. Well, thank you so much. I'm sad that we don't have more time because this was a lot of fun. Thank you, Yann, for this. Again, we're very happy to have you here, and this has been amazing.
Well, thank you so much to the organizer of Khipu, and thanks, Martin, for hosting me and asking interesting questions. Thanks, everyone, for attending. That was fun.
I think we're going to be kicked out soon.
Okay.
Let's see what happens.
Cómo te extraño, mi amor, ¿por qué será?
Hello. Welcome back, everyone. My name is Stephanie Hyland. I'm moderating this second session. I hope everyone enjoyed the first half. So how it's going to work in the second half is we're going to have two speakers talking about applications of machine learning, focusing obviously on self-supervised learning. So they're both going to speak for about 10 to 12 minutes, and then we're going to have a panel Q&A discussion with them at the end. So please submit your questions in the chat, in the Ask a Question box while they're talking, and I will hope to get to as many of your questions as I can during the Q&A. Obviously, we started a little bit late because the first session, which was very excellent, ran over, so we'll also finish a little bit later. So hopefully we'll have a lot of time to have a good discussion. So the two speakers in this session are Enzo Ferrante and Sandra Avila. Enzo will be speaking first, so hopefully we'll get him in a second, and I will just introduce him. So, Enzo Ferrante is a research scientist at CONICET and lecturer at Universidad Nacional del Litoral in Argentina. Enzo leads the Machine Learning for Biomedical Image Computing research line at the Research Institute for Signals, Systems, and Computational Intelligence. His research interests span both artificial intelligence and biomedical image analysis, with focus on deep learning methods. In 2020, he received the Mercosur Science and Technology Award and the Young Researcher Award from the National Academy of Exact, Physical, and Natural Sciences of Argentina for his contributions to the field of artificial intelligence and medical imaging. So I see you're here with us now, Enzo. So if you're ready to present, I will disappear. I'll let you know when about 10 minutes have elapsed.
Okay, thank you very much, Stephanie, for the kind introduction. Can you see my screen there?
Yes, perfect.
Great. Okay, so I try also to time it because I tend to speak a lot. So thank you very much for the invitation. So the Khipu organizers asked me today to discuss a few applications of self-supervised methods in the context of medical imaging. And in this talk, I will be briefly discussing two of these applications in two different problems where we have been working during the last year at the Research Institute for Signal Systems and Computational Intelligence in the city of Santa Fe, Argentina. And the first case I will be discussing is related to a skull reconstruction in the context of cranioplasties. So a cranioplasty is basically a reconstructive surgery that we do to repair a missing part of the skull. That part of the skull may be missing because of different reasons. Maybe you had a surgical intervention, or maybe it was because of an injury. But the idea is that we need to reconstruct that part to then go and use 3D printing technology, basically manufacture an implant that will be put back to cover the hole in the brain, in the skull, sorry. And normally such implants are generated by hand using CAD systems to design them and then 3D print them. And the question I will try to answer today is, can we learn this problem? Well, the process of manually reconstructing these implants is pretty expensive in terms of times, expertise. You need to do a lot of work to do that. So if I ask you right now, how would you train a model to reconstruct this cranial, this implant? Well, most likely you will tell me, okay, give me a bunch of samples composed of images, X, and ground truth annotations, Y, and I will train for you a model following a supervised approach, like a network, like a unit or something like that. Okay, yes, but I'm telling you that this is really expensive to obtain. So can we do something to basically obtain signals from full skulls that were not manually annotated by doctors? And this is basically what we proposed to follow a self-supervised approach to implant reconstruction. And as Yann and Martin were discussing before, the usual approach we take to self-supervised learning is basically we pre-train a model using some pretext task, generally a simpler task than the one we want to do afterwards. And once we have this pre-trained model, then we transfer the knowledge to the downstream task in which we are interested, right? In this case, reconstructing the implant. This is the typical approach, but as it was highlighted in this really interesting survey about self-supervised learning that was published in TPAMI last year, In some applications, the downstream task can be the same as the pretext task without using any human annotated labels. And this is the idea that we will exploit here, a really simple approach to basically train a reconstruction model like this one, but without using human annotations. And how do we do that? Well, that's what we proposed last year at MICAI in this paper. That was work led by Franco Matskin, one of the PhD students that I'm supervising at the university. And it was also collaboration with Virginia Newcomb from Cambridge University, Ben Glocker from Imperial College. And what we proposed here was a really simple idea that is basically, okay, let's simulate a virtual craniectomy. So before I was talking about cranioplasties, that is when you put a part of an implant into the skull to cover a missing part. The craniectomy is basically the opposite. It's when you remove a part of the skull. And so what we did, it was to propose a virtual craniectomy procedure to basically simulate these craniectomies using full skulls. Full skulls are cheap to get because you just take computed tomographies, do some really basic thresholding operation, and you get the skull from there. And so with that, we get a lot of information, and by using our virtual craniectomy that basically consists on using different shape, different templates to remove parts of that skull, take the difference, this will be now our image X, the skull with the missing part, and we will have the extracted bone flaps as our ground truth that was virtually generated. So we will only need full skulls to do that. And the self-supervised concept here comes from the fact that we don't need human annotations, but we are just producing them and using the full images as self-supervision. So we use different types of shapes. I'm not going to go into the details of the paper. The paper is there. I'm going to leave the presentation, the PDF then, so that you can check the pointers I'm giving in the talk to some works. And in this work, we basically evaluated two different approaches. So as I was telling you, these skulls are extracted from computed tomographies. Yes, we do first a simple thresholding to extract them. And then in the paper, we discussed two different approaches to the same problem. Basically, we are interested in estimating the flap, but we can follow two different alternatives. One is first reconstruct the full skull and then take the difference, and that's your final flap. And the other option is to directly estimate that. So all the experiments are there. We compare different approaches, different methods that were trained using our simple virtual craniectomy procedure. And we found out that the direct estimation is the best way to basically estimate these flaps. The take-home message I want to take from here is that when we can, sometimes we can simulate pretext tasks that are really similar to the downstream tasks. And then if we can do that, then we can train a model following a self-supervised approach like this one that will be useful. And we could even fine-tune the model in manually annotated cases if we have them. So this is the code. You can go there. This is Franco, the PhD student. And these are some works related to this. If you are interested in this problem, there is right now going a challenge on this competition on cranial implant reconstruction that is going right now. We participated last year. It's pretty fun. So if you have ideas to explore there, you can go to the challenge and try them. This is the first case I wanted to discuss today with you. And then there is a second case that is completely different application. This is medical image registration. It's another problem in medical imaging, which consists in, we have a source image, I, we have a target image, J here. And if I overlap these two images, most likely they are not well aligned. Yeah, they can come from different patients or the same patient at different times. And the idea of image registration is basically, I want to estimate a deformation field, which is a vector field at the end, that indicates how should I move every pixel from the source image so that it deforms and matches the target image J. That's the problem of image registration. And if I want to, the question I would like to ask you now is, what if I want to learn to perform image registration? What would I need? Well, I will need images and I will need ground truth annotations, right? And these ground truth annotations will be these deformation fields that I would like to infer. If I if I follow a supervised approach, a standard supervised approach to model this problem from a learning perspective, what could I do? Well, I could have triplets like this, okay, where I have my unlabeled images and my ground truth annotations. And basically, I can pass them through some kind of encoder-decoder CNN, like a unit, for example, produce a deformation field, a vector field, and compare this vector field with the one I should have produced. And basically take, I don't know, mean square error of that and just minimize this loss. Okay, but if I told you it is difficult to annotate the missing parts of the skull in the previous problem, can you imagine how difficult it is to deform an image by hand and annotate that? That is really difficult to do. And so we want to have an approach to image registration that does not require ground truth deformation fields for training. And there is where the self-supervised idea comes again into my mind. And let's go back a couple of years ago when we were doing image registration, following the conventional approach, let's say, which was the following. So a couple of years ago, if I wanted to do image registration, I would just take the images I and J and pose it as an optimization problem, where I'm basically exploring a space of possible transformations, possible deformation fields, and trying to minimize a similarity measure that tells me how well aligned the deformed source image and the image J are. We also use, in general, a regularization term that imposes certain geometrical constraints on the deformation field to avoid foldings, for example, and undesired properties on this deformation field. We optimize it using an optimization algorithm like gradient descent, for example, and we get the optimal transformation. But we used to do that for every couple of images, for every pair of images we wanted to register. You give me a new pair of images, I solve this problem. You give me a new pair of images, I solve this problem again. And this was really time-consuming.
You're at 10 minutes, Enzo.
Okay, I should be done in 2 minutes.
Perfect.
So here it comes, how can we solve this problem from a self-supervised approach? And this was proposed by many works kind of at the same time, around 2018. We call it self-supervised approach, and also we call it in the medical image community an unsupervised approach, where we now have training data samples composed only by unlabeled images. We don't have the ground truth deformation field. And what do? We take the images, we again pass them through an encoder-decoder CNN that produces a deformation field. But instead of computing a loss function with respect to a ground truth deformation field, what we do is we use this deformation field to warp the source image. We basically deform this source image using what are called spatial transformer networks that were proposed around 2015, and they have nothing to do with the transformers we were discussing before. But it's basically a differentiable warper. It's something that can go into a neural network that is differentiable and that can take an image, a transformation, and apply it. So I get the deformed image here, and now I can compute a similarity measure with the target image that I'm interested in matching. And that's all, because I can train this model now end-to-end, because everything is differentiable here. And so this can be trained using a lot of pairs of images. And at the end, I will have a model that can now register new images. And the good thing about it is that I don't need deformation fields. So it was obtaining supervision signals from the images themselves. I didn't need to have ground truth deformation. So these were the works in 2018 that proposed this initial idea, and we have worked and built some studies on top of this, and I'm leaving here the papers in case you are interested on seeing these works. There is also the source code by Lucas, who Lucas is another one of the PhD students who is working on this problem. And if you are interested in trying these ideas, you can go and check his repo. So I hope by showing these two examples, I convince you that we can use these self-supervised methods in the context of medical imaging and take advantage of the images themselves without using these ground truth annotations. This is who we are, and thank you very much.
Thank you very much, Enzo. So as a reminder to everyone, we'll have questions at the end. So if you have any questions, please put them in the question box, and I'll ask them after Sandra's talk. So I'll now introduce Sandra. Hopefully we can add her to the live stream here. So Sandra Avila is an assistant professor at University of Campinas in Brazil. Her current research interests include machine learning and AI techniques for healthcare, sensitive media analysis, precision agriculture, and other tasks. Her research on skin image analysis, classification, synthesis, debiasing has been recognized through several academic awards, including Google Research Awards for Latin America in 2018, 19, and 2020. In 2020, she participated in the BRICS Young Scientist Forum representing AI research in Brazil. Her passion is to encourage more girls and women to pursue STEM fields. So Sandra, if you're here, please, we should add her to the live stream, and please, go for it.
Yeah.
I'll take myself away.
Okay, can you hear me?
Yep.
Yep. Okay. Thank you, Stephanie, for the kind presentation, and thank you, Khipu, for inviting me and give me the opportunity to talk about our results and problems on self-supervised learning for skin cancer analysis. So I'm joining to Enzo and how to convince you that self-supervised learning is a good idea. So. Skin cancer, why do we care? And I mean, why do we care in Brazil? Why do we care in Latin America? Why do we care in the world? Yeah. Skin cancer is by far the most common of all cancers. It's by far for the most common of all cancers. In Brazil, it accounts for 33% of all diagnosed cancers. The good news is that if the melanoma, the most dangerous type of skin cancer, is detected early, the chance of survival is about 99%. So early detection really saves lives. The standard method for the examination of the skin cancer is based on pattern recognition. So it makes sense to apply deep learning to learn skin lesions patterns. But let's move in the presentation, but keep these numbers in mind, please. Our research lab, called Reason for Complex Data, has worked on melanoma classification since 2014. Our team is responsible for remarkable results associated with deep learning and skin cancer, not only in Brazil, but also in the world. We are very excited that our research has been published on newspapers and communicated on TV news. In our research, we are dealing with problem in different ways, skin cancer problem in different ways. We've researched on data augmentation by use GANs, for example. By the way, in our first paper about GANs, we generate impressive synthetic images, but at the time, it seemed like a good idea. And now in our latest paper to be published in CVPR 2021, our research suggests caution in their adoption for medical applications. We've also researched bias on skin lesion data sets and how to mitigate it. And now our next step is to advance skin lesion analysis with self-supervised learning and regard a more realistic scenario. I will talk about that. So that's an overview of our pipeline. And to be clear here, we are not introducing a new self-supervised model. We are evaluating for self-supervised learning different pipelines considering field-labeled images. We first evaluate self-supervised pre-training and followed by supervised fine-tuning in skin lesion data sets. And then we evaluate a two-step pipeline. We perform an extra pre-training staging, varying the contrast loss, supervised or self-supervised version, but fitting in the skin lesion images, and then perform a supervised fine-tuning. But today, I will show the results for the usual pipeline, self-supervised pre-training for the supervised fine-tuning. And also, we compare with the supervised baseline. So here we employ the most applied skin lesion data sets, the International Skin Image Collaboration, the ISIC, and the demoscopy 7-point criteria evaluation data sets. And the first 3 data sets contain demoscopy images. That means the images are captured using our demoscopy. And the last data sets contain clinical images. And that means that the images are captured using our smartphone, for example. In a melanoma versus benign setting, we evaluate 5 self-supervised pre-trained models on ImageNet: Sinclair, Suave, PO, Infomin, and MoCo. And using our ResNet as backbone, we only vary the learning rate for fine-tuning. Only the learning rate for fine-tuning. And for supervised pipeline, we perform a grid search varying learning rate, batch size, balanced batch, the absence or the presence of balanced batches, learning rate schedule, and other things. And to achieve that results, where is the results? Here, we try harder. So the message here is that it seems that it's easy to get good results using self-supervised learning, and we need to do a lot of experiments to get a good result using our supervised pipeline. For the next 3 slides, we report the results for top 5 models for each approach, for self-supervised and supervised approach. And all the self-supervised, as you can see, all the self-supervised model outperform their supervised pipeline in a distribution test set and out of distribution test set. And here we are using the ISIC 2019 data set, and the training data set has 15,000 images, so it's not so much, yeah? And for a more realistic scenario, for example, to use those models on a public hospital or a community healthcare clinic, those results are very impressive because you're using on 10% of labeled the images. So that means 1,500 images. And more hard scenario, we are using only 1%, and 1% here, that means only 150 images. Yeah. Let's back to the slide that I asked you to keep in mind. The numbers that I asked you to keep in mind. For Black people, the survival rate is not 90%, it's only 66%. So we know that deep learning has the potential to save thousands of people has the potential to save people from skin cancer each year, but while putting others at greater risks. So our data-driven solution should be inclusive. Everybody knows that, yeah? But as Dr. Jenna Less says, if you are only training to look at something in one color, we won't recognize it in another color. And common conditions often manifest different on dark skin. The problem is that, another problem, is that the skin lesion data sets barely contain dark skins. And the Fitzpatrick scale is a numerical classification scheme for human skin color. So for the ISIC 2018 data set, a paper explored the distribution of the skin tone in data sets, and they found that they have only 3 images of dark skin here. With the exception of but we have some data sets, 2 data sets in fact, and with exception the PAD of data sets, the Brazilian data sets, and the Fitzpatrick 17K, none of the publicly available data sets include skin type or skin color labels. The PAD of 20 data sets contain Fitzpatrick skin types labels, but very few images of type 4, 5, or 6. For example, for type 6 of skin color, they have only 1 image here. And the Fitzpatrick 17K was collected from 2 online dermatology atlas, and the images are annotated with Fitzpatrick skin types. But this data set that we present in CVPR 2021 has some ethical issues, problems. The image contain, for example, the name of the medical doctor. I think this is not a good idea. And there are naked children for some images. So I don't think I need to say anything else about the data sets. And now we start to evaluate our model in black skin lesions in a collaboration with Dr. Camila Rosa. Our results are very promising using those data sets, her data sets, yeah. But we can show the results not yet. Okay, we are very recent results, so we have to evaluate more those results. And last but not least, sorry, many thanks to my all students, and I think that's it. Thank you.
Thank you, Sandra. And thank you, Enzo. So we're now in the Q&A section. So at this point, please, yes, type your questions into the chat. I'm gonna kick it off with questions for both of our speakers. I'm gonna ask some specific individual questions, and then I'll ask you some questions for both of you. So starting with Enzo, I'm very interested to know, I think you mentioned it at some point about the different types of shapes that you tried in your virtual craniectomies. I'm curious, I imagine that the origins of craniectomy in the normal world could be quite varied. So did you find that you had to sort of like carefully choose what types of virtual craniectomies you had to do, or what was the impact of that?
Yeah, this is something that in general, I think it's pretty important when you do self-supervised learning. I mean, the sense of the data augmentation you use, because basically this is a form of data augmentation there, right? We use a lot of different templates. And we observed that when we were incorporating more variety to this set of templates, that was helping, in fact. We evaluated our model using real craniectomies, which have also a particular shape. And also we tried to simulate in our last experiments that were not in this paper, but things that we are doing right now, try to simulate craniectomies that really look like the real ones, not just random shapes that we are using to remove them, but also taking into account how these craniectomies are done. And that seems to also be helping now. So this challenge, I'm telling you, the auto-implant challenge, I think it's a really interesting place to go and check for these details, because we were a lot of different methods competing in this. We didn't win, by the way, but it was fun to be there, and they're doing it again now this year, so it may be a nice venue to check.
Great, yeah, hopefully people can check that out. I'm not sure if you're able to drop links in the chat, but I'm sure the Khipu organizers will help to share any information afterwards.
Yeah, I will try.
Yeah. Okay, great, thank you for that. So Sandra, I'm curious, I'm not, so I work in health applications, but not in dermatology. I'm very curious, so it looked like in the results you were showing the impact of using self-supervision, it's improving the performance, but the performance is already quite high, it looks like. So I'm curious, what's the clinical impact of improving the performance more? Is there a certain accuracy or AUC that it needs to exceed before it could be more useful to clinicians? Or could you speak more about the clinical aspect?
Okay, thank you for the question. I would say that the high accuracy is because we're training only in the almost white skin lesions, yeah, fair skin lesions. So, and if you train in evaluating the same data sets, the results are very, very high. But when we change the data sets, the results drop. I think we can show. I show that in the presentation. So if we start to change the type of the image, for example, for the endoscope image to clinical image, the results drop a lot. And the problem that, and this is the real world, because it's more difficult to obtain the demoscope image than the clinical, because the clinical you can take a photo with a smartphone and ask for the and show to the physician and ask for the results. But the problem is that it's not a problem. It's the problem. It's the how can I say that? It's the methodology problem. That using a demoscope, we have more information about the data. So it's easier to get better results using our demoscope images. But using the clinical images, you don't have a lot of information. So we have more or other kind of information about the images. So I think that's the results.
Yeah, great. Yeah, that makes sense. I think this challenge when your test set might look a little bit different to your training set. This comes up obviously a lot in machine learning, but especially in healthcare where the types of data sets that we're using might be a little bit different to reality. I'm curious to sort of ask Enzo about this. So in the world of like medical imaging or like CT skulls, do you expect a lot of variability in the shapes of skulls that you encounter or across populations?
Yeah, actually, I think, well, there are many factors, but for example, age may be one of the most important there. We haven't done any study, but this is something we also have in mind, about what happened if the model that we have trained now for reconstructing these craniectomies, we use it for different ages. And most likely we will get some kind of bias because of the way we have trained it and the heads we have used for training. But I think by using different data augmentation strategies, we can again trying to gain some kind of invariance to that. For example, I don't know, even changing the size of the heads, right? For during training and just reshaping them, making them smaller, and in that way you can account for small differences in shape and these kind of things. But yeah, I expect heads to be different, and then I mean we have used this model in the hospital. We are collaborating with hospital. The images we are getting are coming from actually the hospital at University of Cambridge, but we haven't really deployed the system in a real pipeline. This is something that will be done, I hope.
Yeah, for sure. That's always the end goal for all of this applied kind of work. So question for Sandra. I'm really curious. You mentioned at the start of your talk that you've done some work on GANs and the limitations of them in the sort of medical applications. Could you speak a little bit more about that? Because I know earlier Yann LeCun kind of mentioned, GANs didn't end up being that useful. So I'm really curious to know what your findings were as well.
Okay, thank you. In our first paper, we proposed a GAN-based method to augmentate the data, and the idea is to get better classifiers. And we only try one method, yeah, and simple experiments. I think I can say that. And now we try a lot of experiments and change a lot of things, and we see that there is no much difference, and we can't improve our models using data augmentation by using GANs, and we hypothesize that the problem is that we need more rigorous experiments and try more. And if we try to do more experiments analyzing everything about the not about the GANs but about the problems, the results are the same. So the GANs didn't help, and worst, the GANs are learning the bias of the data sets.
Yeah, that's basically the opposite of what you want to happen when you're doing data augmentation.
That's dangerous. That's dangerous.
Yeah, for sure. Maybe a quick follow-up question for Sandra, and so I'm not forgetting about you. You talked a lot about these different data sets, and you mentioned some of the serious limitations in them in terms of diversity of skin tone. So what's the solution? Are there efforts to create new, better data sets with better representation? Should we try and use machine learning? Maybe not GANs, maybe something else?
I think we didn't try using GANs for medical applications, and now I think it's clear for us. But we evaluate only in skin cancer classification problems, okay? But for our data sets, I think we have a problem with data, but it's not only about data, it's about people. And I think we have to discuss more about ethics and maybe less. It's really important to discuss about techniques, but I think we should discuss with our students and society. It's not a problem of, it's a problem machine learning. The problem is that deep learning, it's amplified that. And to solve the problem, we need more data, we need better data. And if we are trying only in white skin lesions, this model doesn't work on Black people. So I think the problem, it's not about only the data, it's not about on the model. And to get more representative data, we should discuss ethics. And this is not a problem for machine learning.
Yeah, for sure. This is something I want to believe that the machine learning community is becoming much more aware of in recent years. This is something that, there's more workshops and keynotes and so on the topic, and I think people are starting to learn and better appreciate that our field does have these big challenges. Okay, we have a question for Sandra. I'm gonna pause that for a second and ask another one for Enzo. So the methods that you were describing for like image registration and the reconstructions of skulls, can this be applied to other imaging problems, either within medicine, maybe other like bone reconstruction or other types of applications?
Well, for example, for the medical image registration model, one of the studies that I was posting at the end, one of the works we did, it was to study how these models adapt across different organs, across different anatomy. So what happened if you train one of these models, for example, with brain images, and then you try to use this model to register cardiac images. And of course, there is a change of domain there. There is a shift of domain, which reduces performance. The models can still be used, but you can, the fact that this method is self-supervised in this case, it just learns from the images. You don't need any annotation. So you can even learn from a single pair of images and solve the problem for this single pair of images. This will work. It will take more time, of course. But another thing that you can use is that use a different anatomy as pre-training, for example. You train on heart and then you fine-tune on brain. That helps a little bit as well. So this pre-training, in this case, helps. In the literature of medical imaging, there is a paper really interesting by Adrian Dalka and other people from MIT, where they call this amortized inference. I think this relates to the theory of optimization and other ideas, but basically the idea is that you pre-train an optimizer with some data, and then once you get the two new images, for example, you just fine-tune on these images and solve the problem for these images. This is faster than doing the training from scratch, let's say. And so in that sense, the model can kind of adapt, especially because we don't need ground truth. So you can just kind of overfit to your pair of images, but well, at the end, this is the pair of images you want to register, right? So you can just overfit and solve the problem. But pre-training there helps a lot, so the model can be used from one image, from one anatomy to another. Yeah.
Yeah, that makes sense. It's an interesting setting that you're kind of happy to overfit, that you can,
this is something we discuss a lot in this paper, I'm telling you. So it's like weird. Why would I like to? Well, but at the end, this is the pair of images you want to solve, and you can do it because. So yeah.
Yeah, that makes sense. Okay, so question from Rodrigo for Sandra. Are the skin cancer detection models being clinically used? And what are the challenges in applying them to the real world? I think it's a little bit similar to what I asked you before, but I think this is more like, are these models actually getting used on real people already?
Sorry, can you repeat the question?
Yeah, sure.
Okay.
Yeah, the question is the skin cancer detection model being clinically used? So I don't know, is there like an app that you can download one of these models and try it out on yourself?
No.
Or, yeah, probably not.
No way.
Yeah.
No, this is very dangerous. No, it's not a good idea. We need the solution put out a number, and we need a medical specialist to interpret that number. And there are more information than the model can do. So no, it's not. The idea is not put in an app and use it by anyone.
Okay. Is it something that a clinician could use to assist them?
Yeah, that's the idea.
Okay, but this it's not implemented.
And to say that, so you need to go a specialist or not, and that's the idea. Because in Brazil, for example, we have a lot of regions and city that doesn't have a dermatologist, so a specialist in skin issues. So clinicians maybe using an app and say that, oh, okay, you can go to our doctor.
Yeah, that's a really interesting point, and it kind of leads me naturally into a question I want to ask both of you, which is to do with the opportunities or challenges for applying machine learning, self-supervised or not, to Latin America specifically, because I think that's something the audience will certainly be interested in.
Yeah, I don't know. I can comment on. I mean, what I tried to do when I came back to Argentina a couple of years ago and started to do research here, it was to also connect with local institutions, and I was basically looking for problems, interesting problems to solve. So in that search, I found, for example, an Argentinian startup which is called Entelai, which they develop like deep learning models for medical image analysis in the field, and they go to the hospitals and they install it. And so with them, we have a really rich discussion because they are bringing into the hospitals, into the clinic, what we are doing in the laboratory. So I think this is a nice way, linking with local institutions, like in this case, a company, but I am also supervising PhD students who are working in the hospital. So Candelaria and Agustina are the two PhD students with whom I'm working, and they are developing tools in the hospital that are going to be used, in this case, in Hospital Italiano de Buenos Aires, are going to be used there. And this is fantastic because we are thinking about problems they face and trying to bring solutions using some of the technologies and the methodology we have been developing. So I think this is not particular to Latin America. This is in general, but it's nice to, when you do applied machine learning, try to link with local institutions, not only international institutions, but also local in your country.
I just add a comment here. I think it's the same answer, but in a different way. Data is very precious. Yeah, everybody knows that. And I think we are not using our data to solve many problems. And perhaps maybe we are missing the opportunity to ask more specific questions about our problems. So maybe this is the way. A good opportunity.
Yeah, totally. I agree with that. I mean, if you go, for example, for NLP, which is not the field in which I work, but there you have, for example, people that are interested in working in Spanish. There you have a really and actually our local version of Spanish, which is pretty different to the one in Spain. And there you have really nice opportunities if you will go into the direction of NLP. In case of medical, well, it's a bit different, but as Sandra is saying, we have our problems. Demography is different. People are different here. So we are in the lab also exploring this, trying to even create data sets here with local institutions representing our population and not only the population from the north. So I think something important also for us.
Yeah, thank you. So you touched on it a little bit, but obviously this is the sort of applied machine learning session, and you've both described very applied projects. So for people in the audience who may have been working in, let's say, traditional machine learning, who are interested in going into more of the applied side, what kind of advice would you give them for starting off or for thinking about having a career in this space? Maybe Sandra, you can go first.
I can go. Yeah. I think that the first advice is choose an application or a problem that you are motivated to go harder, to work harder in that problem. And there are many papers about everything. Yeah, people are discovering new tricks every day, but they are don't panic, enjoy the community. And I think it's my first advice. Yeah.
Yeah, for sure. The amount of research which is done all the time can be extremely intimidating for everyone. So I think no matter your career stage, that's probably good advice. Enzo, your thoughts?
No, I completely agree with Sandra. I think, people who have been doing machine learning, like maybe more methodological developments, and want to bring this into the applications, well, I think you have to find a partner in general, like somebody who is an expert in that domain that you want to apply this. This is important, and it's not easy sometimes. But in general, for example, I'm working with images, and whenever I go and I give a talk about images, people come with new problems. Like they say, I don't know, pictures of tomatoes, and I want to detect, if they are okay or they are going to perish. So this kind of stuff, like random stuff, you will get so my recommendation would be go there and talk to the community, basically, in these events, in different type of events. Yeah, I would say that.
Great. I have a quick follow-up question of sorts for Sandra, and then we'll have one final question. So if people have burning questions, please ask them now. So Sandra, this is maybe a slightly self-serving question for me, but from your bio, you mentioned you're interested in supporting, women and girls in STEM. So do you have any specific recommendations or advice for female researchers in machine learning or applied to machine learning?
Look for role model. I think it's important to see, and the role model, for example, for me, it's not someone that is really far from here. It's for example, my colleagues, my colleagues that are they're also professors, and that is very important. And to know that we are not alone. And I think that's the big advice. Look for someone that you can be inspired for that person.
That's awesome. Okay, so I'm looking at my. Okay, I'm sorry. I'm looking at my feed of questions coming in. So one small question for both of you again. We can run over a little bit. I hope that's all right. What are your experiences and tips with working with an imbalanced data set? I think this one might be from the audience. If either or both of you would like to respond.
Go ahead, Sandra, if you want. You have been working.
You can go.
Okay. Yeah, I mean, we have been working with, recently last year, actually, we worked on a problem where we were analyzing, for example, how gender imbalance in medical imaging data sets affect the quality of the predictions, basically doing some kind of fairness studies on that. And I think, because I completely agree with what Sandra said before. I mean, data is one of the problems. Models are another problem, but also people are the problem when you work with this kind of, because sometimes we don't realize that we are actually dealing with an unbalanced data set. In this case, we simulated the imbalance. Basically, we had a balanced data set, so we could simulate the scenarios and see how the model performs in men and women, and see how that affects the performance of the models, and make some studies on fairness. But in some cases, when the teams that are developing these models are not diverse, and they do not include people from all type of backgrounds, ethnical, sexual orientation, even sometimes, because when you are dealing with models of language and this kind of stuff, is also important. I mean, there are many situations in which, if there is not that person in the team, you're not going to realize that you are dealing with an unbalanced data set. So I would say, I mean, we have been doing some work more technical on that aspect, but I think, people are also, I just wanted to bring that back, because I think it was really important what Sandra said before. And yeah, you have to be careful with the metrics you use to measure the quality of your results, of course. I mean, it's not the same working with balanced and unbalanced data sets. So yeah, there is a lot of literature about right now, and things are going, a lot of research going on in that direction.
Great. Okay, I think we must come to the final question. So I'd like to just close with a little bit of looking to the future, and ask you what are perhaps upcoming methods or applications or problems in your area that you're most excited about, either for self-supervised learning or within the medical space.
I can go first. Now, I'm very excited about self-supervised learning. Because because of the results, the idea of I don't need to try hard to get good results, it's really good. Yeah, and with self-supervised learning and few-label images, we really get there. So this is amazing. It's really amazing, and especially for medical image processing. That's our problem that you are discussing here. And I think transfer learning has enabled development of many applications. I think now that self-supervised learning is going to boost that development much more. And we should try first self-supervised learning. I'm not here to defend self-supervised learning. It is not the case, but the results for our case, it's very impressive. So that's why I'm very excited.
Yeah, Enzo?
Yeah, I mean, there are many problems in which we are interested, actually. So, but I think one of the directions in which I've been working, and I really want to continue working on, is trying to deal with different data structures. Not only, I mean, graphs, for example, is a field that I've been working in my PhD, and I'm also interested right now. How can we also bring these ideas from self-supervised learning, for example, to when we are dealing with different data structures, like graphs in this case, how we can take advantage of these in the context of geometric deep learning, for example. This is something I'm really interested in one of the lines. And another thing is that of fairness, basically. I'm coming back with the same again, but this is something that really have been in my mind during the last year, and how we can create more fair and accountable, creating models that will work for everybody and not for only a portion of the population. I think from the technical side, we can do also a lot for that.
Yeah, that's a really great sentiment to finish with. So thank you both for your wonderful talks and for your fantastic questions. Thank you to the audience for asking the questions and for your participation. I think we are going to now hand it back to Fede, who's going to close out the session. So thank you both again.
Thank you.
Thank you.
All right. I think I was muted. Yes. So yes, I just wanted to close thanking you all for participating and for connecting with us today, and also to announce that we have an event prepared for next month already, which is we're gonna be talking about fairness and biases in AI, and we will hear about this topic from Emily Denton, Luciana Benotti, Laura Alonso, and Shakil Mohammed. So we're extremely excited about discussing this topic and looking forward to seeing you all next month. And with that, just thank you for participating. We have a few ways to keep in touch in the meantime. We have a website where you can also see the past events. We have a Slack where we can also keep discussing about these topics and any topic. We are also always looking into ways of making these events better and more useful for all of you. So we will be sending a feedback form soon. So please do add your thoughts and opinions and suggestions for regarding the format or the topics or anything that you think would be useful. And lastly, if you'd like to keep in touch, you can follow us on Twitter, and we'll be posting news and announcements over there. So yeah, thank you all for participating, and hope to see you next month.